All right, let's get right into it. We're going to talk about one of Apache Spark's most powerful and, let's be honest, coolest features. Its incredible ability to just not fail, or rather, how it recovers when things go wrong. Okay, picture this. You've been running this massive job for, I don't know, hours, maybe all day. You're watching the progress bar, it hits 99%, and then, bam, a worker node just dies. That feeling, right? That sinking feeling in your stomach? Do you have to start all over again? With Spark, the answer is, thankfully, a huge no. And we're going to break down exactly how it pulls that off. So, how does Spark pull off this magic trick? Well, it all comes down to its default recovery plan, and I love this analogy. Think of it as a recipe, and this special recipe has a name. It's called Lineage. So, what is lineage? The official term is directed acyclic graph, or DAG, but recipe is just so much better. It's basically a super detailed instruction manual. Spark is, well, it's meticulous. It writes down every single step you took, every filter, every map, every single transformation that led to a piece of data. So, get this, if that data disappears, Spark doesn't panic. It might not have the finished cake, but it has the exact recipe to bake it again from scratch. Okay, let's make this real. Forget the theory for a second. Look at this simple chain of events. Step 1, we start with a bunch of numbers in an RDD. Step 2, we filter out the odd ones, keeping only the evens. Step 3, we take those even numbers and we double them. And finally, step 4, we filter again for anything bigger than 50. See? Each one of those actions, that's a line in Spark's recipe book. That's how the lineage gets built, step by step. So here's the absolute key takeaway. When a node goes down and a chunk of your data just evaporates, Spark doesn't freak out. It stays totally calm. Why? Because it doesn't need a backup of the data. It has something way, way better. The instructions to remake that data perfectly, right from the original source. And this is how it all plays out. The main driver program notices, hey, partition 5 is missing. It immediately goes to its recipe book and finds the instructions for partition 5. Now here's the really smart part. It doesn't remake everything. It only recomputes the single partition that was lost. The rest of your data is totally fine. And the best part for you do nothing. It all happens behind the scenes automatically, and your job just keeps on chugging along. Okay, so Lineage is awesome, right? It's Spark's built-in superpower. But, every superpower has its kryptonite. It has its limits. So what happens when that recipe isn't just a few steps, but gets really, really long and complicated? And yeah, this is where we run into a bit of a problem. Think about it. Following a recipe for a simple cupcake is quick. But what if your recipe is like a 1,000-page long cookbook for some crazy complex dish that takes days to prepare? That's exactly the challenge we face with super long lineage chains. And that's the crux of it. I mean, sure, the recovery is automatic, which is great, but rerunning 100 different complex steps just to rebuild one piece of data, that could be just as slow or even slower than when you first ran the job. It becomes this massive performance bottleneck. And that's when we, the developers, have to step in with a more advanced tool. That tool is called checkpointing. And the analogy here is just perfect. Think of it as pre-baking half of your super complex recipe and sticking it in the freezer. You're basically telling Spark, hey, save this intermediate result to a safe place, like HDFS or S3. What this does is create a brand new starting point. It's like telling Spark, look, if anything goes wrong from this point forward, please don't go all the way back to raw flour and eggs. Just grab that thing from the freezer and start from there. It literally cuts the recipe, the lineage, in half. And this comparison just says it all. Look at the before scenario on the left. A failure means you have to replay that entire, painful, long history of transformations. But on the right, after we've set a checkpoint, a failure just means we're loading that saved data from disk and picking up right where you left off. We're talking about a recovery time that can go from hours down to minutes or even seconds. It's a total game changer. Okay, so let's recap. We've got Lineage for our basic automatic safety net. We've got checkpointing for those really long, complex jobs. But there's another set of pro tools we can use to really dial in that balance between raw speed and rock-solid safety. And that brings us to caching. So, caching, or as you might hear it, persisting, is pretty straightforward. It's just you telling Spark, hey, I'm going to need this piece of data again soon, so keep it handy, would you? Most of the time, we do this for a massive speed boost, right? Reading from memory is just ridiculously faster than recalculating everything. But, and this is the important part, how you choose to cache that data can have a huge impact on your fault tolerance too. So Spark gives us a few different ways to cache things, a few different strategies. The default one, memory and disk, is a great all-rounder. Fast, but if you run out of memory, it'll spill over to disk. Then there's disk only, which is slower, but it's your best friend when you're working with data sets that are way too big to fit in memory. But for what we're talking about today, for true resilience, check out that one in the middle, memory and disk 2. You see that little underscore 2 at the end? That little number is everything. So what's so special about that underscore 2? Well, using any of the storage levels that end in underscore 2 tells Spark to do something brilliant. Save a copy of each data partition on a completely different computer in the cluster. Now, think about what happens when a node fails. The driver doesn't even need to think about lineage or recipes. It just goes, oh, that machine is gone? No problem. I have an identical copy of that data right over there. And your job continues practically instantly. This is the holy grail. It's the ultimate mix of blazing speed and bulletproof safety. Wow. Okay, we have covered a lot of ground, haven't we? From the basic recipe of lineage to the freezer trick of checkpointing, all the way to replicated caching. So let's boil this all down to one single pro-level takeaway, the kind of thing you'd say in an interview. Okay, here it is, the whole strategy in a nutshell. Spark's default, its primary method for fault tolerance is lineage-based recovery. Simple. For jobs with really long lineage chains where that recovery gets too slow, you bring in checkpointing to save your progress. And finally, for those critical data sets where you need both top-tier performance and near-instant recovery, use caching with replication. That's it. That's the whole playbook. So, I'm going to leave you with a thought. Now that you know about these tools, about lineage, about checkpointing, about replicated caching, how is that going to change how you design your next Spark job? Because it really isn't just about making it run, it's about building it to survive anything that gets thrown at it. Thanks for tuning in.